So in previous sessions we looked at big O notation, which is the upper bound. Here we look at big omega, which is the lower bound. So definition is almost same for t of n, a non-negatively valued function t of n is in the set of omega g of n if there exist two positive constants c and n0 such that t of n is greater than or equal to cg of n for all n greater than n0. So meaning is for all data sets big enough, the algorithm always executes in more than cgn steps. So big omega is the lower bound, therefore for all data sets big enough, the algorithm always executes in more than cgn steps. Right, so this is the lower bound. So as it indicates, so the algorithm executes in more than cgn steps. So big omega example, c1n squared plus c2n. So c1n squared plus c2n greater than or equal to c1 n squared for all n greater than 1. So t of n greater than or equal to cn squared for c equals c plus c equals c1 and n0 equals 1. So therefore t of n is in omega n squared by the definition. So we want the greatest lower bound. In the previous one, big O notation, we selected the tightest case. Now big omega, we want the greatest lower bound. So we find the greatest lower bound, so that is an important point. So for Tn equals c1 n squared plus c2n, the example. So if we write c1 n squared plus c2n here, c1 n squared plus c2n here, so we have to write something which is greater than or equal to that, and it should be the greatest lower bound. So we have to write c1 n squared. So we can write 1 here, we can write just n divided by 2 or something like that, but that is not the greatest lower bound. So we have to write it in the same class which is closer to this, so that is n squared. We have to write something here, and we have to guarantee we should meet this condition greater than or equal, plus it should be the greatest lower bound. So that is the maximum thing that we can write here is c1 n squared. Therefore Tn is in omega n squared by definition. So theta notation. So when big O and omega meet, we indicate this by using theta, big theta notation. So definition is an algorithm is said to be theta of h of n if it is O h of n and it is in omega h of n. So that is the tight bound. So a common misunderstanding is confusing worst case with upper bound. So upper bound refers to the growth rate, worst case refers to the worst input from among the choices for possible inputs of a given size. So upper bound is not the worst case. So upper bound refers to the growth rate. So the growth rate of an algorithm. So growth rate is when the data size increases or decreases or increases, what will happen to the complexity. Worst case is, for example, if you want to sort a particular set of numbers, if the number set is already sorted, that is the best case. If you want to sort the numbers in the ascending order, but the numbers are in the descending order, so that is the worst case. So worst case refers to the worst input from among the choices for possible inputs given size. So the worst input, that means if you want the particular number set to be sorted in the ascending order, but the given number set is in the descending order, so that's the worst input. So worst input is the worst case. So worst case refers to the worst input, But in contrast, the upper bound refers to the growth rate. So that's the growth rate of an algorithm. So when the data size increases, how the algorithm will perform. So don't confuse worst case with upper bound. So we looked at theta notation. So these definitions are extremely important. Big O, when big O and big theta meet, we indicate this by using, when big O and omega meet, big O and omega meet, we indicate this by using theta, big theta notation. So definition is algorithm is said to be theta of h of n if it is in O h of n and it is in omega h of n. So these definitions are important. So in exams you have to write it as it is. That's the end of the session.